what we're going to be going over here is an example where we're going to be maximizing our marginal product revenue, and we're going to be doing this using linear programming, and we're going to have a nonlinear objective function here that we're going to be maximizing. So this is the situation here. The company is going to offer deep discounts on its product here when they first introduce it here, and then they're going to eliminate those deep discounts, and what they're going to do is they're going to increase the price of the product here, and in doing so, after eliminating those deep discounts, they intend to boost or increase the sales revenue here, because they're going to be making more sales revenue here when they have eliminated those discounts. So when you're doing that here, you're using linear programming. You're going to have a revenue modification that's going to be required here in the programming. So what you're doing here is you're increasing your marginal revenue. That's where marginal revenue is going to increase by some percentage here of the original value of our maximum sales. So that's what we have to calculate here. And really what we're going to be looking at here, by looking at this exponential function that we're going to come up, we're going to have really multiple solutions here on our different product quantities that we're going to be looking at. So that's really what we're trying to get at in this example here. Okay, so this is what you're going to do here. When you're talking about this increasing our marginal revenue here, you're going to have to come up with some, it's based on some integral portion here of the change here of your quantity of your sales here over some price of your sales. So let's go down and let's look at what we're talking about. And before we do that here, our example is going to be based on this deep discounts going to be eliminated up to 50% here for this example here. That is, we're going to have a 50% reduction in our sales price when we start out, and we're going to eliminate that percentage here as we move up our for our example that we're going to look at. So let's understand what's going on here. Okay, so first for our example here, we're going to have three different products, product P, Q, and R here, and we're going to have a sales price here, and a sales price that we want to end up with here for each of those products. P, we're going to have a sales price here of $90, Q, $100, and R, $70. And it's going to be based on those maximum original sales quantities that we're going to be looking at. And we're looking at, for P, 100, Q, 40, and R, 60 here. Okay, so again, when we're talking about this marginal revenue here, it's really based on an integral, and let's understand what's going on here. It's not very difficult to make the calculations, but understand how it's done here. So first off, let's just look at our first product P here. So we're talking about, we want to get up to a sales price here of $90, but we're going to start out with a 50% discount here. So that gives us 50% times 90. That is going to give us an initial price here that we're looking at $45 here. And then it's based on those sales quantities that we're looking at. In this case for P here, that maximum original sales quantity we're looking at is 100. So if we take the integral of that based on a P here. So really when you're talking about integrals, you're looking at areas, and in this case we're really looking at our marginal revenue that we're talking at. So you just take your 45 here, that first, okay, let's look at it up here. That's our last sale here is going to be $90 here. But the first sales we're starting at $45 here. So we're going to take 50% of our $90 to get to 45 here. And then our original sales quantity here that we're starting with is 100 here. So that's how we set up our integral here. And really the integral here is just taking, and you just take your number of your product P here, and you raise it by the exponent of 1 here. So you're ending up with a squared, exponential squared value here that you're squaring P to, but you divide it by that exponent 2 here. So we square it, P, product P here, the quantity of our product P, and then we just divide it by 2. So for our integral here, how we end up with it, you just take 100 times 2, you end up with 200, divide that into 45 here. So that gives you your coefficient here, 0.225 times P raised to the power of 2, or P squared here. Okay, so we're going to, we've done it for P here, so just for Q and R, we do the same thing here. So for Q, we have a sales quantity here, we're a sales price here of 100, and our original sales quantity at 40. So 50% of that 100 gives us 50 here, divided by our sales quantity of 40 here, and just go through that integral here, and you're going to come up with your fractional amount here is 0.625 Q squared here. And same thing for R here. You're just going to take your original sales price here is 70, so 50% of that is going to give you 35, and then our original sales quantity here is 60 here. So you end up with a fractional amount here, 0.292 times R squared here. So that's your integral or exponential increase here that you're looking at as far as your marginal revenue is concerned here for this problem. Okay, so that's looking at how we do our account for our marginal revenue. Okay, so now let's go look at our linear program here. So really what we're looking at is our marginal product revenue here is a function of sales, and our objective function here is to maximize our profit here. So this is what you're doing here. So this is our objective function, and just look at our revenue portion here. Remember, we started out with, we're talking about sales quantities. Look at in terms of P, Q, and R here. We'll start with P. Well, we want to get up to a sales price here of 90. We started out with a 50% of that, so we have 45 times P plus that integral amount here, 0.225 P squared here. That's going on. That's what's showing. And the same thing for Q. Well, we started out with, we want to get up to a sales price of 100, so we take 50% of that. We start out with 50 Q, then add its integral amount here, and then for R, we want to get up to sales price of 70 here. We start out with that 50% amount here, so we're going to start out with 35 times R here plus its integral amount here, 0.292 R squared here. And then we're going to deal with one other thing in this problem. It's going to be materials. We're going to have 4 different materials that we're using on these products here, and we have to subtract them because they are a cost as part of our objective function. They are the cost portion here. Okay, so let's look at that here. So we're going to have, again, looking at a parts layout here, a parts per unit here for product P, Q, and R here. And there's going to be 4 different materials that are required. Material 1, 2, 3, and 4 here. So just got it laid out in a table form. That cost here, the whole unit cost here in dollars used here for our different products here. For material 1, it's going to be 20. Material 2, $40 or $20 again, and material 3 is going to be $20. Material 4 is going to be $5. So that's the unit cost here. So we just put that into our object of a function up here, and just as the coefficients, our cost units here, those coefficients, you just bring them up here and you'd be subtracting those, and then you take them times each of the materials here. 20 M1, subtract it, minus 20, whatever material M2 that number we're going to be using here, subtract that, and then 20 M3 and minus 5 M4. Just take it off your table here. Your material, unit cost, do the subtracting times each of those quantities. So that's what we're going to have to solve for. We're going to have our revenue portion up here, and then what we're looking at, our marginal revenue portion up here, and then we're going to subtract out that material cost. Yeah, naturally, you could have other costs that are concerned here, labor and so forth and that, but we're just looking at it in terms of materials so you get an understanding of what's going on here. Okay, so that takes care of our objective function, but now we got some constraints. We'll look at our constraints here on those materials. We're going to have, just take a look at your parts per unit here. Whatever number of parts per unit here, there's going to be your coefficients here and your constraints for M1 through M4 here. So looking at M1, let's look at that P. We're going to use 1 part here for P and none of the other parts here. So P, coefficient of 1 here. But in this case, when you're talking about material, you have to subtract that here. P minus M1, because you want to come up with an exact amount in this case when you're looking at linear programming, and it has to be greater than or equal to. Actually, it's going to be set equal to, and we're not going to get into that detail here, but you have to understand that you're going to have to set it up as an equal to here when you set up any slack variables or entered into your linear program here. It's got to equals 0 here. Really, you're taking whatever material you have, using your product here, you're subtracting it, and you should come up with a 0. You're just balancing everything out here. And then for M2, what we had P1 and 1 part P, 1 part Q, so you get P plus Q, again, minus M2 here is going to be greater than or equal to 0. You can't have less material in your product here, and we're certainly not going to put any more material in a product, so we're going to just set that as equal to when we set up our linear program. Same for M3 here. We're going to have 1 of Q, 1 of R here. So Q plus R each got a coefficient of 1, minus M3 is going to be greater than, actually going to be equal to 0, and P M4, just one M4 material here, is just using product P here. So P minus M4 is going to equal to 0. Okay, so that's our constraints here for materials, and we'll look at the other, we're going to have some constraints on some manufacturing that we have, or machining manufacturing, or machine operations we have as well here. But before we get into that, let's just understand what this function is looking like here. Okay, so this is really what we're talking about, that marginal revenue here. As we increase our product here, we're going to come up looking at just terms of quantities of 100 here. You can see we start out, and it's got this increasing function here. It's convex up here. And I got it for P here. I got that line here for P. I got one for Q here and one for R. It's an exponential nonlinear function here when you're talking about nonlinear programming. And as far as when you're actually, if you calculate this out by hand here, when you're dealing with those marginal revenues here, just understand here, we have to go through that integral to determine this marginal revenue here. So this is our profit function, increasing our marginal revenue for P, Q, and R here. So just an area curve here in 2-dimension. It gives you a little idea what's going on here, and when you're talking about this marginal revenue, so looking at it here in a sketch gives you an idea rather than just looking at numbers here. But this is the problem that we're going to come up against here. We're looking for the optimal product mix here to maximize the profit here, or maximize our marginal revenue here. And what we're really going to come up with is you really have different multiple solutions that you're going to come up with. Our maximum profit's going to be pretty close for our different solutions here, but between P, Q, and R here, we're going to have different quantities, and that's really what we're getting into on this program here. And then finally, if we go down here and look at it in just 3D here again, just to give you some perspective here, looking at it on a graph or a plot here, our marginal profit here is that objective function f of x that we looked at here. Again, it's nonlinear here for P, Q, and R. Sort of gives you an idea what's going on here. Okay, so now we'll continue on with our problem here, and we're going to look at some more constraints, and then we'll look at our solutions and what we end up with, solutions and things that we have to be looking for. Okay, now for our production capacity constraints, and they do with machining that's required here on our different products, P, Q, and R. And P, Q, and R here are going to go through 4 different machines here, A, B, C, and D. And what we're going to look at is the use of the capacity here for each of those products here by machine here. So first off, for our total available capacity here for each of our machines here, A through D, we have 2,400 minutes here for each of those machines. And then the use of the capacity here, let's just look at it in terms of our first row here. For machine A, P is going to use 20 minutes, Q is going to use 10 minutes, and R is going to be using 10 minutes on a per unit basis here. And then we do the same for B, C, and D here. Okay, so now for our machining capacity constraints. So all we do is take our coefficients off our use of capacity here by machine, by our product here. So let's just look at for machine A here. So P would put 20 times P here for whatever number of P we're going to produce, plus that comes off our use of capacity here. And then for Q, we just take 10 times Q plus 10 times product R here. And it's got to have to be less than or equal to 2,400 minutes. We can use less than that amount here, but we don't have any more here, so it has to be less than or equal to. So for our linear program, we're not going to put an equal to it. You just remember, keep your constraints here as less than or equal to for any slack variables or whatever you have to do when you're setting up your linear program. And then the same here for machines B, C, and D. Just take the coefficients off your capacity use here for each of those products and just move them down into your constraints here. And then just remember less than or equal to. So our maximum capacity here, that constraint was that 2,400 here. So that would be our constraint here as far as our maximum capacity. And then you just take those coefficients off your usage table here and add them to your constraints here. Okay, so that's our machining capacity constraints. Now if we look at it over here, just get an idea looking at it in 3D, remember those machining capacity constraints here. So we really have 4 different planes that we're looking at because we've got the machines A, B, C, and D here, represented by those different planes here. And I'm just showing, giving you an idea what we're looking at here when you're talking about this linear programming here and how you're going to have to maximize your profit here. So that's what you're going to have to deal with here. So then you're going to take those constraints here, plus you'd have your material constraints, however you want to figure those in, either in your capacity constraints here or into your profit function here. So we got that marginal profit, that objective function. Remember, we looked at it was nonlinear up here. You match those two together here, you marry those two together, and you're going to get some solution where you're going to have your maximized profit here. And this is where we're going to be looking at that solution to see the different quantities that, to come up with a solution here, you're going to really have different quantities. You're going to have, for the same value, you're going to have different quantities that we're going to look at. So just marry those constraints with your objective function, your marginal profit function, and you're going to come up with something that looks like this here in 3D. And then again, just remember here that solution here is based on that revenue function here, that marginal increasing revenue function here, less any of those material quantities. Okay, so now we'll go and we'll examine our solution here to this linear programming problem that we're looking with marginal revenue. All right, now for our solution here, and remember we had that profit function where we've got those three different products, P, Q, and R here, where they have an exponential nonlinear increase here in the marginal revenue, and really it's a convex curve here. What we have to do is we have to determine the optimal product mix to maximize our profit. Okay, so looking at it here in 2 dimensions for those XY plot here for our profit here. So this is the case here. When you're dealing with these exponential functions here or curves either going upwards or downwards, whatever they may be, you have to use some caution here. When you're maximizing either a convex or minimizing a concave curve that you're looking at when you're using linear programming, and we'll look at it here in terms of numbers here. And what I'm doing, I've used MapleSoft, their optimization package here, and the function would be NLP or nonlinear programming solve function here. So what I've done here, this is our objective function that we were looking at here, and then we had our marginal revenue here, less our material cost here, plus the constraints we would have included in it. Now, this is what we want to maximize. So what I've done here, I've really run 8 different trials here to demonstrate the problem that we have. So I got our trial runs shown across the top here, and then along our rows here, we have our initial points for P, Q, and R, those different products. Those are the points that we supply into our software package. And then the software is going to give us our solution here for P, Q, and R. So P, Q, and R here in yellow are our initial points. P, Q, R here in green here is the solution that's supplied. And then I've got the profit calculated down here that the program gave us. So first off, for our first trial run here, and this is where I wouldn't have entered any values here, and this is just what the software package would have given me, and it would have started at P, Q, and R here at 0 initial points here for those, or quantities if you want to look at it. And what it would have given me back here as a solution would have been P, 0 quantity, no quantity of product P, but Q and R would have been 40 and 60 respectively, and we'd had a profit here of $3,351 here. Okay, so that's if I've done nothing and just relied on the software package to come up with the solution. But now let's look at our different trials here. For our second trial, and it doesn't matter here, for the initial points I just use 30, 30, 30, but you could go 40, 40, 40, just equal amounts, or 50, 50, 50, and you're going to get a solution here where you're going to get, instead of 0 here that we have for P with doing nothing here, it would have given us a quantity of 26 for P, and then Q would have been 40 and 60, the same as we have here for our initial solution, but with doing nothing here, or starting with our 0 in points. So these initial points, that's where that software starts out at, and it moves from in both directions here, just to understand that. And then the profit here based on this second run, it moved from 33.51 up to 35.11, and that's really due to the fact that P moved it from 0 to 26. Okay, so you can see the problem we have here. When we supply those, when we rely just on the package itself here, and we don't put in any other initial, check any other points here, we can come up with different quantities and different profits. So just looking at our third run here, I put in P 140 and 0 here for P, Q, and R, and it would have given me back the same thing here in quantities, P 140 for Q and 0 here for R. Fed me back the same solution. Same initial points gave me the same solution. But then looking at here, the same thing, I just 90, 40, and 0. Here, the package is going to give me 26, 40, and 60. These 90, 40, and 0, that's really the initial points. And the software is going to go on both sides, work on both sides of those initial points. So you can just see what you're getting here when we look from 30, 30, 30 to 90, 40, 0, and we're getting the same amounts here and the same profit, 35, 11 here. Okay, and then for the fifth run, I go 90, 0, 50, and you can see what's going on here. I get P, Q, and R 80, 81, 16, and 16. And then looking at the sixth trial run here, I put in 50, 20, and 60. I get the same numbers, 81, 16, and 60. And you can see the variation here between P, Q, and R here. And P, Q, and R, my inputs versus the outputs. The outputs are the same. And then for the seventh run here, I put in 30, 20, 60. And again, I'm getting a 26, 40, and 60, very much the same as what I did here for my first trial run here. But I got completely different points here. Comparing my initial points are different here, but I got the same output here and the same profit. And just looking at my last trial here, my eighth trial, again, got some 10, 0, 30. It's going to be 26, 40, and 60 here. See, totally different points here, but I'm coming up with the same result here with the same profit in terms of quantities here, quantities for each of the products here versus the profit here. So you have to use caution when you're using these linear programs, when you're dealing with those concave and convex functions here, just to make a point. And you're going to have to use some judgment here, because you can see you're getting numbers all over the map here as far as what they're suggesting as the solution points between the product P, Q, and R. Depending on what your initial points are when you supply those in the program. And what I mean by supplying them in the program, you actually enter them into the software package that you're dealing with, and then it gives you the solution output. Okay, so you can see the broad range of values you're coming up with, and you are coming up with some different profit levels as well here. So this was my initial point, 33.51, with the quantity that the software gave me, P0, Q40, R60, and you can see the different results I had depending on the different initial input points here. Okay, so just be aware of that, and you have to use some judgment here when you're coming up with the optimal product mix to maximize your profit here. Okay, and then finally, just looking at it here in terms of the linear programming setup here, and I've got it laid out in matrix form. However you do this, however your software is, you're going to have some matrix that you're going to be loading in, or some values are going to load in here. So I got a 8 rows here by 7 column matrix, because I'm dealing with P, Q, and R here for the products, and then we have those 4 different materials, M1, M2, M3, and M4 here. So for my matrix here, for my coefficients here sitting up at P, Q, and R for a machine capacity, I just take those coefficients and feed them into my matrix here. And then we have what they call slack variables. You're going to have a whole bunch of zeros in here for M1, M2, M3, and M4 here, because I'm not dealing with those here when we're talking about the machining capacity in this case here. So, and what I'm doing here is I'm taking this constraint here, this less than and equal to a 2400 here, off my machining capacity constraints here, as my looking at the constraint here as what maximum amount I can be looking at. So that's my matrix here as far as my machining capacity constraints. Just remember my slack variables here for M1, M2, M3, and M4 by quantity, by column here. I have just 0 amounts here. And again, P, Q, and R, that's just coming right off the maximum capacity constraints above. And then moving down here for my material constraints, you can see that all I'm doing is taking those coefficients here from my constraints and putting them into my matrix here for each of those columns here, P, Q, and R here. You can see I just have coefficients here 1 because that's what we're looking at. But the thing that we have to deal with in this matrix itself is these, what they call, we have slack variables up here, but we have surplus variables down here, and those are those negative 1, 1, 1, and 1 here, that diagonal amount, and that's based on those material constraints. We're subtracting those, or what we're doing here is we're really taking an equation here where we're setting it equal to 0 here, because we want to just put in enough material, and we don't want to put in extra material because we don't want to have enough. We have to have just enough material, and we don't want to put in an extra amount of material here. So just remember, you just take those negatives, so you can see you're subtracting it out here, and you're setting it equal to 0 here is my vector. What we're looking at is my vector, or what we're trying to look as our maximum amount here. We're just setting it equal to 0. But just to make a point here, for looking at that M1 column, we have a minus 1 here. And you can go down here and see it in the constraint, minus M1 here. And the same here for M2, M3, and M4. And then just moving up to our matrix here. Let's just look at our matrix here. M1, I had that minus here on that row for that material 1 here, that row 0, 1, 0, 0. 1 here for P, 0 for Q, and 0 here for R. And then you're just moving to M2. I had a minus 1 here again. We're subtracting. And if you go down to our constraints, you're going to see 1 here for P, 1 here for Q, and then 0 zeros. But you end up with this diagonal here at those minus 1s, because really what we're doing here with the minus 1s, we're setting these constraints, this maximum amount of constraints, equal to 0, or equal amount here, and we're equaling to the 0 amounts here. So that's what we end up with, those surplus or negative units here of 1 for each of those materials. Okay, so basically this is when you do whatever your software package is, or whatever you're doing to make these calculations here, you're going to have to come up with a matrix of this sort here that we just went over. So you're going to have your different variables here as your columns, and then your different rows here are going to be those constraints here that you're dealing with. In this case, we had the machining constraint here, the material constraints here, and then you have to deal with what they call those slack variables here. We have 0 slack variables here on top, but we have those negative surplus variables here for our materials here in our bottom rows that match our material constraints here. And then you're going to have some vector amount that you have to put in here for whatever maximum you're allowing for each one of those rows that you're looking at here. Okay, so that'll pretty much summarize our topic here with this linear programming when we're looking at those. In this case, we looked at maximizing a convex function or minimizing a concave function. You have to be very careful here in determining your results here, as you know, based on the trial runs that I looked at. Okay, so that'll summarize our discussion.